Hello folks, this is Jag with another video presentation. This particular presentation theme is shift registers. Right, just before I do actually move on to the theme of this presentation, I'd like to actually conclude on the counters module. I know strictly speaking it shouldn't actually be in this presentation, however I've just kind of we covered a 3-bit synchronous counter. I think we left it on counters. This is just an extension. This is a 4-bit synchronous modular counter. Remember what modular means? It just means modulus counters. It just means that it counts up to the maximum value and then starts again. So if you've got 4 bits, that's 2 to the power 4, which is 16 minus 1. So you've got to count from 0 to 15. And this is a circuit using JK flip-flops. Now it's a synchronous counter. Remember, it's a synchronous counter. So what does synchronous means? Synchronous means that all the clock is applied to all flip-flops simultaneously. This reduces the propagation delay that we observed when we look at asynchronous or ripple modulus counters. So this is the circuit. Now it requires 2 AND gates. Two input AND gates, and we'll have a look on the truth table why that is the case. For the A, the least significant bit, that's just set to toggle on the negative edge of the clock. So 0 is memory and 1 is toggle for a JK flip-flop, but this just toggles on each negative edge of the clock pulse because these flip-flops are negative edge triggered. Flip-flop B has the output Q of the first flip-flop connected to the JK input, just like before. Flip-flop C has the ANDed outputs of A and B connected to the JK inputs of the third flip-flop. And flip-flop D has the ANDed outputs of B and C connected to the JK inputs. See there? And there. At those points, D is allowed to toggle. And just kind of continue this way, you can make an n-bit modular synchronous counter. Okay. Now today's theme is shift registers. I say today, this presentation's theme is shift registers. Now before we actually move on to shift register, let's just look what a register is. A register is a device for storing memory, in most cases storing a bit pattern. Whatever that bit pattern may do is kind of irrelevant almost. It's got numerous applications. For example, on the PIC microcontroller you've got ADC con registers which control the ADC. Likewise, there's numerous applications of registers. Could just be memory in a computer. Now for registers, in particular memory registers for just storing bits of data, D-type flip-flops are used quite a lot. D-type is data latch flip-flops. And here I've kind of showed a simplified block diagram of 4 D-type flip-flops connected together to store 4 bits of binary data. Each bit stores either a 0 or a 1. Now you'll see that the flip-flops themselves have a clock input, a load input and a clear input. Now what we're assuming is that the registers are a part of a larger system. Now in a larger system you may have a clock which is running at a particular frequency, particular clock rate speed. However, you may require the data storage in your registers to be at a different rate than the system clock. So the system is kind of a common entity which services all parts of your circuit, whatever that circuit may be. However, your data transfer might be required to actually operate at a different rate. Clock may be, I don't know, 1 kilohertz. That's not a typical clock frequency, it's normally in the megahertz, isn't it? Clock frequency may be 1 kilohertz, which is a clock period of 1 millisecond, if I'm correct. Now you may want the actual data transfer to be a lot kind of slower than that. You may want the data to be entered and transferred every 100 milliseconds, for example. For that reason, we've actually got a load input as well. Now the load input can be used in conjunction with the clock input. So when the load is high and on the next active clock pulse, data could be transferred into the flip-flops. Another reason why we need load is if the flip-flops were just clocked using the common entity, there's a chance that every time the clock enabling pulse occurs, whatever that is, negative edge we've been looking at previously, then the data is transferred into the flip-flops. Now, there's a chance, because there may be noise in the system, electrical noise in the system, that a wrong data bit may be input into the D-type flip-flop. So you may have entered 1100, and after a while, because of noise being generated internally in the system, in the circuit, you may end up with 0000. So that data has been corrupted, and you've got kind of junk values in there. The load control input will kind of eliminate that to a certain degree. So a load input is a common kind of feature in these types of registers. Likewise, a clear as well. So you can clear the flip-flops when you want to. So just clear it on. It doesn't have to be at the mercy of the clock. It could be out independent of the clock itself. So you can just clear the data 0000 when you want to, so you know it's fresh, and then load new values in. Now, in terms of the clock, how it's connected to the flip-flops, it could be connected two ways. It could be asynchronous or it could be synchronous. Remember, asynchronous means that all the flip-flops aren't clocked simultaneously. Synchronous means all flip-flops are clocked simultaneously. So if the load is synchronous, that means on the next active clock pulse, data will be stored. If the clear is synchronous, on the next active clock pulse, data is cleared. If it's asynchronous, it's independent of the clock. As soon as load is high, data is transferred. As soon as clear is active, I should say, is not high, then the flip-flops are cleared. Okay, so that's the common kind of features of the register. This is a register. There is no shifting involved in this whatsoever. We will look at the shift registers, but this in itself is just a plain register for storing data and reading from it whenever you want to. Okay, I'm just going to read out these, even though I've covered them in detail. I'm going to read them out. So clock is a common entity and may be at a faster rate than you want the data transfer. Data will only be transferred when load and next clock pulse is active. Clock can be asynchronous or synchronous. Flip-flops will be cleared when clear is active and the next clock pulse is active if synchronous. Okay.